So some features of such flywheel based energy storage systems we will just now discuss. Energy loss can be minimized by magnetically levitating contact-free bearings. So typical bearings used in typical applications is contact-based bearing. So the shaft is on bearing support and the shaft is rotating over these bearings. And there is rolling contact between the bearing and the shaft, okay, which has significant amount of friction. But if the bearing and the shaft is magnetized, then there can be the bearing section and the shaft can be contact free. The magnetic forces ensure that there is repulsive forces between the bearing and the shaft, which is keeping the shaft away from the bearing while holding it at a steady location. So this creates contact free bearings which have significantly lower friction. Energy loss can also be minimized by enclosing the flywheel in vacuum to reduce frictional drag losses. Okay. So another issue with a moving system is there is frictional loss due to air drag. So if you locate them in vacuum, then it can reduce this frictional drag induced losses. So typical places where flywheels are good are for rapid charging and discharging. Applications that help maintain the quality of power for renewable energy based grids. So the idea of flywheel is when there is a sudden spike in supply over demand, you put that extra energy into the rotational energy of your flywheel rim. Okay. And then when there is a sudden spike in demand compared to supply, you use that rotational energy and transmit some amount of rotational energy quickly out of the flywheel and back into the electrical system. So basically these are connected to your electricity generation shafts. The flywheel shaft is connected to the electricity generation shaft. When supply is high and demand is low, you are connecting the flywheel shaft to the generator shaft to transmit some of its rotational energy quickly to the flywheel shaft, where it is stored for a certain period of time, usually a short period of time. And then if the supply suddenly decreases and the demand spikes, you again re-engage the flywheel shaft with the generator shaft and transmit some of the rotational energy of the flywheel into the generator to keep the generator rotational motion constant. So the generator rotational motion is is being kept relatively constant to provide high quality power that matches with the demand. So small scale demand supply fluctuations can be made uniform. Okay, so if the supply is going up and down, just as it happens during the intermittency effects of a wind turbine or a solar power plant, you can use the flywheel system to stabilize the shaft velocities and hence give a uniform voltage and amperage supply to the grid. Okay, so this helps maintain the quality of power of the renewable energy based grids in the system. So this is a very different type of an application compared to hydroelectric or compressed air, pumped hydro and compressed air storage, where you are trying to adjust large time scale alterations in demand and supply. These are short response. Flywheel is specifically designed for short response energy storage systems. So usually have short self-discharge times in the order of minutes to an hour, minutes to hours at most, as rotational energy tends to dissipate away due to losses. Okay. So these usually have short self-discharge times in the order of minutes to hours as most, as rotational energy tends to dissipate away due to frictional losses. Even though you are reducing frictional losses due to drag, etc., that by creating vacuum, creating superconducting bearings or contact-free bearings, still there is significant frictional losses, and hence these have short self-discharge times. Okay. High cycle efficiencies of the order of 0.9 if cycle times are rapid. Okay. So within this short self-discharge time period, so within time scale of minutes and an hour, if a flywheel will actually deliver very high cycle efficiencies of the order of 0.9. So 90% of the energy that is being transmitted to the flywheel can be recovered back. So this is compared to say 40%, 30% that is present in pumped hydro and compressed air storage. In this case, you can recover back up to 90% of the energy, provided that the cycle times are rapid. So that is, you are not hitting the self-discharge times of several minutes of an hour or so, then the efficiency will drop very quickly. But under typical applications of fast response of seconds and minutes, you will get very high cycle efficiency, that is, you are recovering most of the energy you are giving to the flywheel. So cycle times, however, cycle efficiencies can drop to below 0.5 if cycle times approach the order of 1 day. So this is basically what we are speaking of, low self-discharge times. If you are cycling, that is the time between absorbing power and transmitting that power back is approaching 1 day, then your cycle efficiencies can drop below 50% because you are going to the self-discharge time limits for such a system. Okay. usually energy storage capacity is low. So you won't get gigawatt hour kind of energy storage capacities, but energy absorption and transmission rates can be very high. So what we are saying is, even though it is absorbing relatively small amounts of energy, the rate at which it can absorb and transmit this energy back to the main system can be quite high. So it can, even if it absorbs say 100 kilojoules for example, it can transmit this, absorb and transmit this 100 kilojoules within a time frame of a second or a fraction of a second. So you can have very high power absorption and power generation, power transmission rates for such flywheel systems. Okay. Flywheel systems are also used in regenerative braking of high speed trains. So there they absorb part of the energy released during braking and releases this energy during acceleration. So high speed trains have to stop in stations and then again have to start accelerating very quickly. Okay. When it's decelerating due to braking, a large part of the kinetic energy of the train is being lost. So part of that energy is being transmitted to these flywheels which is storing that rotational energy, and then it's transmitting this rotational energy back to the train when it's accelerating out of the station. So this is called a regenerative braking system, because it's the braking itself has a regenerative section driven by the flywheels, where it's storing the energy lost during braking and then releasing that energy when the train needs to accelerate. The maximum energy density of storage depends on material density and maximum allowable tensile strength. So there are two basic factors: what is the density of the material and what is the maximum allowable tensile strength of the material, and over these two factors we can determine what is the maximum possible energy storage density for your flywheel. We can show that E by M max. So the maximum energy stored per unit mass of a flywheel system is equals to sigma tensile max by 2 rho. Okay. So this is the specific energy density. The maximum specific energy density is equal to the maximum tensile stress of the material divided by 2 rho. Okay. Where sigma tensile max equals to rho omega square r square. Okay. The maximum tensile stress, whatever the value is, will be given by rho into omega square r square, as we discussed before. Okay. So E by m max, we can put rho omega square max square here equals to r square omega square by 2, or it can equals to this term also, the rim radius and the rim omega. Similarly, we can also show E by V max. So this is the volumetric energy density, this is specific energy, this is volumetric energy density, equal to sigma tensile max by 2. So rho omega square r square, the maximum value of this allowed by 2. Okay. So this is the relationship of specific energy density, and this is the relationship of volumetric energy density. So based on this, then we can create a chart of the various flywheel materials and the maximum energy storage density for these materials. So material, then density of the material in kg per meter cube, followed by sigma tensile max in megapascals. Pascal is Newton per meter square, so megapascals is 10 to the power 6 newtons per meter square. Then the specific energy density E by m max in kilojoule per kg. So first material is stainless steel, SS. Its density is 8000 kg per meter cube. So remember, water's density is 1000 kg per meter cube. So density of stainless steel is 8 times that of water. Its maximum tensile stress is 600 megapascals. So the specific energy density of such a flywheel material will be 37. Next, if we take aluminium alloy, so remember this is the value divided by 2 rho, so you can get 37. So you put 37 here, and this gives r square omega square by 2. So that will give you basically the given on r, what is the omega value that you can get maximum. Okay. Then you can look at aluminium alloy, which is a lighter metal. So it's 2800 kg per meter cube. So 2.8 times denser than water. Its tensile strength is somewhat lower, around 400, but still because its density is lower, this one here, so you will get higher specific energy density of 71. Okay, so almost double. Okay, energy storage density. Remember, you can compare this, you can also do this one here, sigma tensile by 2, so this becomes 300 and 200. So the volumetric energy density is basically half of the sigma tensile max. Okay, correct. So if you look at 200 kilojoules per kg, and if you remember for example kilojoules per meter cube, if you look at the case for storing water, there you are getting much more, significantly more amount of energy per meter cube. Okay, so you are getting much lower energy densities in a flywheel system compared to pumped hydro system. So that comparison you can also make, okay, for these kinds of systems. Then you can have glass fiber. Here its density is 2500, close to aluminium, but your tensile strength is significantly large. So we are now looking into modern materials like glass fiber, non-metal systems. and you are now getting specific energy values of 400 kilojoules per kg. Okay. Then you have another modern material like aramids, which have even lower densities of 1400 density and 3000 tensile strength. So you are clearly getting around 1070 as the kilojoules per kg as the maximum mass based energy density that a flywheel based from aramid fibers have. Then you get carbon fiber, a very common material that is being used nowadays, with density of 1800 and tensile strength of 6000 megapascals, giving you the specific energy density of 1700 kilojoules per kg. Okay. And an even more modern material, graphene, which is under extensive research now for many applications. Density is similar, 1800 like carbon, but your tensile strength potentially, and this is still in the research stage, is 10 to the power 5. So it's like 100,000 megapascals. So you are getting specific energy values of 28,000 kilojoules per kg. So we can see that with the advent of modern materials, you are getting significantly higher specific energy densities as well as volumetric energy densities, which kind of are proportional directly to these ones in modern flywheel systems, which make them viable as a fast response energy storage technology in renewable energy grids. So there is a significant amount of exciting research that is happening now in flywheel energy storage based on modern materials, modern structures, etc. That is due to its application in this fast response renewable energy grids. Okay. You can also have, and this is the last part we will do before finishing today's class, you can have flywheels of arbitrary shape. We just looked at rim type flywheels. Flywheels of arbitrary shape, your expression of E by M becomes K into sigma max by rho. Okay. Where K equal to 0.5 for rim type flywheels, the typical conventional flywheels, but K can be of the order of 0.9 for constant disc type flywheels. This is a modern design. So again we have an advanced design of something called a constant disc type flywheels, where this K value can be increased from 0.5 to 0.9. Okay. So that again increases the specific energy density. So this kind of concludes our discussion on the flywheel based energy storage systems, which is the last of the mechanical energy storage systems. We see that it is used for fast response systems to maintain the quality of power, and we see there is a lot of innovations in flywheel both in design and materials that can help make it a viable technology for the next many decades and more. Okay. In next class, we will shift our discussion from mechanical energy storage systems to electrical energy storage systems, where we will look at capacitors and their modern variants. So thank you for listening, and we will see you in the next class. Thank you.